Hey there, science fans! Welcome back to another mind-boggling episode where we unravel the mysteries of the universe. Today, we're diving into a brain-bending phenomenon that has puzzled scientists for ages, the Mpemba Effect. Named after a Tanzanian student, Erasto Mpemba, who first observed this curious occurrence in the 1960s. Imagine this. You have two identical containers, one filled with hot water and the other with cold. You might think that the cold water would freeze first, right? After all, it's already closer to the freezing point. You pop them both in the freezer side by side and wait. The cold water should logically freeze faster, but sometimes the hot water beats it to the punch. Which one do you think will freeze first? If you guess the cold water, you're not alone. Most people would agree with you. Common sense says the cold water, right? But here's where it gets interesting. Under certain conditions, the hot water can actually freeze faster than the cold water. This counterintuitive phenomenon has left many scratching their heads. Well, sometimes the hot water freezes faster. Bizarre, right? Let's explore why. There are several theories that attempt to explain this strange effect. One idea is that the evaporation of hot water reduces its volume, allowing it to freeze more quickly. Another theory suggests that the temperature difference creates convection currents, which help the hot water cool down faster. Evaporation plays a significant role. When hot water evaporates, it loses mass, and with less water to freeze, the process can speed up. This is especially noticeable in open containers where evaporation is more pronounced. Convection currents are another factor. In hot water, these currents can distribute heat more evenly, allowing the water to cool down at a faster rate. This can lead to a quicker transition to the freezing point. On a molecular level, the behavior of water molecules also comes into play. Hot water molecules have higher energy and are more spread out. As they lose energy and come closer together, they might form ice crystals more rapidly under the right conditions. Erasto Mpemba's observation was initially met with skepticism, but over time, it has been replicated in various experiments. The Mpemba effect remains a topic of active research, with scientists still debating the exact mechanisms behind it. So the next time you find yourself in a freezing competition, remember that hot water might just have a surprising edge. The Mpemba effect is a fascinating reminder that science is full of unexpected twists and turns. Keep questioning, keep exploring, and stay curious, science fans. Until next time, stay cool and keep those experiments going. Our story takes us back to 1963 in Tanzania, a time and place where the spirit of curiosity was alive and well, even in the most unexpected corners of the world. In a modest classroom, a young student named Erasto Mpemba was engaged in a seemingly simple task, making ice cream. But what he noticed that day was far from ordinary. As he prepared his ice cream mixture, he observed something that defied common sense. His hot ice cream mixture seemed to freeze faster than the colder mixtures prepared by his classmates. This was not just a fleeting observation. It was a moment that sparked a burning question in his mind. Intrigued and puzzled, Mpemba approached his teachers with his observation. He asked them why this was happening, expecting a logical explanation. However, his teachers dismissed his question, attributing it to a mistake or a misunderstanding. But Mpemba, with his insatiable curiosity and determination, couldn't let it go. He knew what he had seen, and he was determined to find out the truth. His teacher's dismissal only fueled his desire to understand the phenomenon. Mpemba's persistence eventually paid off. One day, a visiting scientist came to his school. Seizing the opportunity, Mpemba shared his observation and the questions that had been haunting him. The scientist, intrigued by the young boy's curiosity and the peculiarity of his observation, decided to investigate further. Together, Mpemba and the scientist conducted a series of experiments to test the young boy's observation. They carefully prepared mixtures at different temperatures and observed the freezing process. To their amazement, they confirmed that the hot mixture did indeed freeze faster than the cold one. This counterintuitive phenomenon, now known as the Mpemba Effect, challenged existing scientific understanding and opened new avenues of inquiry. The discovery of the Mpemba Effect was more than just a scientific curiosity. It was a testament to the power of questioning and the importance of curiosity in the pursuit of knowledge. Mpemba's story reminds us that sometimes the most profound discoveries come from the simplest questions, and that the courage to ask why can lead to groundbreaking insights. Today, scientists continue to study the Mpemba Effect, exploring its implications and trying to understand the underlying mechanisms. Mpemba's legacy lives on in the ongoing research and the continued quest for knowledge. His story is a powerful reminder that curiosity and persistence are at the heart of scientific discovery. In classrooms around the world, young students are inspired by Mpemba's story. They learn that their questions matter, that their observations can lead to new discoveries, and that their curiosity is a valuable tool in the pursuit of knowledge. The boy who asked why has become a symbol of the inquisitive spirit that drives science forward. Erasto Mpemba's journey from a curious student to a name remembered in scientific history is a testament to the power of perseverance and the importance of nurturing curiosity. His story encourages us all to keep asking questions, to remain curious, and to never stop seeking the answers to the mysteries of the world around us. And so, the legacy of the boy who asked why continues to inspire generations of learners and scientists. In every question asked, in every experiment conducted, and in every discovery made, the spirit of Erasto Mpemba lives on, reminding us that the pursuit of knowledge begins with a simple question: why? One possible explanation for the Mpemba effect is evaporation. When you heat water, some of it turns into vapor and escapes into the air. This means the hot water container starts with less water to freeze, potentially leading to faster freezing. Think of it like this: it takes less time to bake a small cookie than a large one. Section 4. Convection currents, stirring things up. Another theory revolves around convection currents. Heating water creates movement within the liquid. Hot water rises while colder water sinks, creating a continuous circulation. This constant mixing might help to cool the hot water faster, especially near the container's surface, where it comes in contact with the cold freezer air. Section 5. Supercooling. When water gets below freezing, but stays liquid, water has a fascinating property called supercooling. Under certain conditions, water can remain liquid even below its freezing point. Some scientists believe that hot water, for reasons not entirely understood, might be less likely to supercool than cold water. This means the hot water might start freezing at its actual freezing point, while the cold water could dip below freezing before finally solidifying. Supercooling is a phenomenon that occurs when a liquid is cooled below its normal freezing point without it becoming solid. This can happen with water, and it's quite an intriguing process. For supercooling to occur, the water must be free of impurities and disturbances. Even the slightest jolt or the presence of impurities can trigger freezing. At the molecular level, water molecules need a nucleation point to start forming ice crystals. Without this nucleation point, the water can remain in a liquid state even at temperatures well below freezing. Scientists often study supercooling in controlled laboratory environments to understand the conditions that allow it to happen. They use purified water and carefully control the cooling process to observe this phenomenon. As the temperature drops, the movement of water molecules slows down. However, without a nucleation point, these molecules don't arrange themselves into a solid structure, and the water remains liquid. This is different from regular ice formation, where the presence of impurities or disturbances provides nucleation points, allowing ice crystals to form and grow. Interestingly, the likelihood of supercooling can vary between hot and cold water. Some researchers suggest that hot water might be less prone to supercooling because it loses impurities as it heats up and evaporates. Cold water, on the other hand, retains more impurities, which can act as nucleation points, making it more likely to freeze at or just below its freezing point. This means that in some cases, hot water might start freezing at its actual freezing point, while cold water could dip below freezing before finally solidifying. The process of supercooling is not just limited to water. Other liquids can also be supercooled under the right conditions, but water is one of the most commonly studied due to its unique properties. Understanding supercooling has practical applications in various fields, including meteorology, cryogenics, and even food preservation. For instance, supercooling can help in understanding how ice forms in clouds, which is crucial for weather prediction. One of the most fascinating aspects of supercooled water is that it can freeze instantly when disturbed. This sudden transition from liquid to solid can be quite dramatic and is often used in scientific demonstrations. Researchers continue to explore the mysteries of supercooling to unlock new insights into the behavior of liquids at low temperatures. Each discovery brings us closer to understanding the fundamental principles that govern phase transitions. So, the next time you see water, remember that under the right conditions, it can defy expectations and remain liquid even below freezing. It's a reminder of the incredible complexity and beauty of the natural world. Supercooling is just one of the many wonders of science that shows us how much there is still to learn about the world around us.